Have medical problems, but yes. I am.
It's okay.
But I think
I voted the 10,000, so now.
That's right. Yes. Oh.
I don't know. The first time I heard it, I told the gal, I think her mind. It says, no. They got it right, all 97.
A little more likely. Like that. I already know.
Hey. Watch this. You can do it. You can do it. I can do it. I hope. Come on. What am I doing wrong here? Look at that. All right, it's 4 o'clock. We're gonna get started here. We got a test scheduled for, if you look on the schedule, I think it says like Tuesday, March 4th. Or it might be the 6th. Nah, but I don't know what the, so, but March 4 is 6. Probably, I'm thinking 6. That's just what I'm thinking. So we get done with chapter 3. Remember, we are having a test now. So far, we just did chapter 3, 1 through 4, just balancing equations. And in chapter 3, that's how it started out. We were balancing equations. And I said that we are going to come back to this diagram, which we are. Let's review how things dissolve. Things dissolve. In fact, what happens when stuff dissolves? We know that water is polar because they do not share the electrons equally. And we know that the hydrogens are partially positively charged, the oxygens are partially negatively charged. So if we take a salt, in this case, it's potassium chloride. This is my solid. We know that water is going to come in, that water's moving, and that will shake these apart so that when they split up, the negative ion is attracted to the positive hydrogen. The positive ion is attracted to the negative oxide. We know then we can go from this back to the solid here, if we let the water evaporate and these evaporate away, the attractive force between the positive potassium ion and the negative chlorine ion will still come together and you'll get a solid. That's going to happen a lot as the roads are going to get slushy in the next couple of days. It's going to splash onto your car and dry, and then you're going to see the solid form again. If something dissolves, we say it is a strong electrolyte. You are going to get lots of ions in solution. In lab, you're going to measure conductivity. So again, I said the old-fashioned way was to have actually copper wires here with a little bit of PVC over top of them and put it in the solution, see if the light bulb lights up. If you get 0 ions in solution, it is a non-electrolyte. And if you get a few ions in solution, it is a weak electrolyte, a few ions. And vinegar or acetic acid is the correct one. Then we left off, we kind of did this flow chart here a little bit. If it's an ionic compound, it's going to start with a metal ion. If you see a bunch of non-metals together, carbon's a non-metal, hydrogen's a non-metal, oxygen's a non-metal. Most of these are going to be non-electrolytes, no ions. But you can have some acids. If you have a strong acid such as HCl, it's going to split up into ions. If you have a weak acid such as HCN, you're just going to get a few ions. So the terminology for that is this. A balanced equation derived in the usual fashion is called a molecular equation, because it doesn't explicitly represent the ionic species that are present in solution. When ionic compounds dissolve in water, they may dissociate into their constituent ions. Dissociate is this, dissociate into their ions, which are subsequently dispersed homogeneously throughout the resulting solution, and this becomes invisible to the naked eye, right? Now, I dissolved the 2 compounds last week, and I've got them back because we didn't demonstrate them yet. Explicitly representing all dissolved aqueous ions results in a complete ionic equation. 2 chemical species present in identical form on both sides of the arrow are called spectator ions. These ions, whose presence is required to maintain charge neutrality, are neither chemically nor physically changed by the process. So they may be eliminated from the equation to yield a more succinct representation called a net ionic equation. A precipitate reaction is one in which dissolved substances react to form one or more solid products. One product. For our purposes. Many reactions of this type involve the exchange of ions between ionic compounds in aqueous solution, and sometimes referred to as exchange reactions, or double displacement, or double replacement, or metathesis. It's all the same. The extent to which a substance may be dissolved in water or any solvent is quantitatively expressed as its solubility, defined as the maximum concentration of a substance that can be achieved under specific conditions, temperature, and pressure. The units are grams per 100 grams of water. Now, something that, and you could see, there would be a chart of how many grams can dissolve in 100 grams of water. For example, if you just take sugar versus salt, what can you dissolve more of in 1 cup of water just sitting on the table, sugar or salt? Sugar. By far. And what really changes this equation, if you heat it up, you get lots and lots and lots of sugar to dissolve. You heat up salt water, hardly anything changes. I think it's like 40 grams of salt in 100 grams of water. You change the temperature, barely does anything. But sugar, you heat it up, it's a game changer. Okay, I'm gonna do this reaction right here. So here's my two starting beakers that I dissolved last time. And I'm gonna combine them in this beaker right here. So I've changed this up a little bit. So we're gonna change this to, this is copper 2 chloride. And the other thing I'm using is sodium hydroxide. Copper 2 chloride and sodium hydroxide. So the balanced complete reaction or the molecular equation. So copper 2 chloride. And then chloride, Cl-1. So I'm going to need 2 chlorides, right? Now, does copper 2 chloride dissolve in water? Well, here is where if we look at the solubility rules, and this is what you're going to use in lab and in OWL, here's our solubility rules. I believe I don't remember if I screen grabbed these from OWL or not, or the textbook, one or the other, or the lab manual. So this tells you if something dissolves in water. And again, if something dissolves in water, we're saying that water has the ability to split the positive and negative ions apart. So the attractive force between the positive and negative ion is so weak that water can split them apart. If the attractive force between the positive and negative ion is so strong that water cannot split it apart, it doesn't dissolve. So copper 2 chloride, if we look here, it says all chlorides, bromides, iodides, salts are soluble except those containing lead, silver, mercury 1, which are not. Now, this one here says all sodium, potassium, and ammonium salts are soluble. Well, these guidelines up here say almost all. So the only way to do this and make it foolproof is Keys has this diagram, this solubility chart on the back of the pink sheet. This should match up your solubility rules. You should try the solubility rules first, try to find it under the solubility rules. This should back up the solubility rules. So in this case, copper 2 chloride, if I grid this out, well, actually, let's just look at this. There's AQ all the way across 2 rows. AQ all the way across potassium. So the positive ion is here, and the negative ion is here. So we can grid it. And the other one is sodium, AQ, all the way across. But we're specifically looking at copper 2 chloride. We already think it's going to be aqueous or soluble. So if we grid that out, we end up right here is where my chloride is. So copper 2 chloride, let's go back. Copper 2 chloride, it dissolves in water. So I'm going to put AQ. Plus sodium hydroxide. Now, we just looked, all sodium compounds are soluble. We're not going to look up sodium and potassium ever. Aqueous. Arrow. Now, we need to do this exchange reaction, double replacement. We're going to switch the positives. Copper is going to take the place of sodium. So we're going to have copper with a +2 charge. Copper is going to take the place of sodium. And hydroxide, OH -1. So we're going to need 2 hydroxides, right? 2 OHs. We need to put parentheses around that. And we can look that up coming up. And then sodium takes the place of copper. Now, listen, listen, listen. Listen, listen, listen. Just because there's Cl2 here does not mean it's Cl2 on the other side. Do not carry a Cl2. There is a 2 there because copper is a +2, chloride's -1. You need 2 chlorides. Now, over here, sodium has a +1 charge. And chloride has a -1 charge. It's Cl2 here because of the copper, but it's only a Cl here because of the sodium's +1. And that's aqueous. We're not going to look that one up. But we need to see if this hydroxide is soluble. So if we go to our solubility rules, it would be this one down here. Not soluble ionic compounds. Hydroxides and oxides are not soluble except those containing sodium, potassium, or barium. So this right here, solid. Now we have to balance this equation. And to balance this equation, where would we start? Start with hydroxide. That would give us 2 hydroxides. That gives us 2 sodiums. So we have to put a 2 there as well. I think that's balanced. Okay. Now, for a complete ionic, now you're going to write all of these out in lab. And this is this lab gave me liver damage. Oh, wow. I can say it. I'm going to, So I want you to be the rock star of the lab. You got to help your partner. When this splits up, do not write Cl2 minus. There's no such thing as a Cl2 minus ion. Ever, ever, ever. You can only make ions in solution that are on here. And I can guarantee you there is no Cl2 minus. When this splits up, you are going to get copper +2. So now we're going to do the complete ionic. You're going to get copper +2 aqueous. Plus, this 2 is going to give you 2 chlorides. Do not write down Cl2 minus. There's no such thing. Then this right here, we are going to get 2 sodiums. And we are going to get 2 hydroxides. Arrow. Copper hydroxide solid. Plus 2Na plus aqueous. And this 2, we get 2Na plus, and we get 2 Cl minus. I need to put this into my beakers now. I'm gonna, can I color it? I'll see what I can do here. All right. I've got Cu plus 2 in this beaker. And I've got 2 Cl minuses. I'm gonna try to use 4 different colors. Water has these split apart, right? Water has these split apart. That's this blue solution. I used tap water, so it looks a little crappy in there. I didn't use distilled water. This is my other solution of sodium hydroxide. Oops. And we've got 2 sodiums floating around in there and 2 hydroxides. Here's this one. Here's this one. Now, you might say, well, oh, why do we switch to positives? Whatever. I'll explain it to you like this. This is a house party. This is a different house party. And this is a third house party. This couple that were together, copper 2 chloride, arrived at this house party and got into an argument and split up. This couple right here was a couple, got to the second house party and split up. They're all going to walk separately to the third house party. When you get to the third house party right here, whoa, 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 there could be a new attractive force there. Because the question is, at the third house party, is this split up individual here attracted to this split up individual there at the third house party? And vice versa, is this split up person here attracted to this other person here from the first house party? Well, when they enter the third house party, we get this. we get the positive, well, I should say the couple from the first house party here hooks up with the other couple from the second house party here. They go to the basement for their hookup. They go to the basement, correct? For their hookup. And what's left up above is still a pissed off one here and a pissed off one here. There is a new attractive force at the third house party between this one and this one, right? That is why we switch the positive ions to see, is there an attractive force between this ion from this beaker, and that attractive force between those ions is so strong that they're going to come together and water is not going to keep them split apart. This is our solid. This is a precipitate. Now, let's go back up to here to our equation now. And we can lightly X out our spectator ions that are exactly the same on both sides. And that is 2 sodiums, 2 sodiums. So this is like having 2x and 2x, both sides of the equal sign, correct? 2x and 2x, we can cross it out. And then we got 2 y's and 2 y's. These are spectator ions that I crossed out. And then, well, we better show that house party interaction. I stepped talking. I didn't show our interaction. This is copper plus 2. Copper plus 2 aqueous in solution is always blue. So when I dump these together, I'll dump them together in this third beaker here. Now, they don't go to the basement immediately. They chit-chat for a while, and you're going to see that. And that solid in there. If I flip the screen here, you can't see through it. It's kind of a whitish solid in there. But if we let that go for a while, just like letting the night go for a while, end up in the basement, correct? It's going to settle to the basement. If we cross out our spectator ions, then our net ionic equation should be Cu plus 2 aqueous from house party number 1, and getting together with the hydroxide ion from house party number 2, and meeting at house party number 3. Again, now the biggest mistake I see for this liver damage example is students writing this out as a Cl2 minus, and that does not exist. Okay, this would be called the molecular equation, all balanced. Complete ionic, anything that's aqueous, you're going to split it up, and net ionic. Write reactants, write products by exchanging cations, switching to positive ions. Dissociate, write all ions, all soluble salts, strong acids, and strong bases. Split them up. Dissociate, split them up. Now here's another liver damage example. I see this. Look at what this says. Do not break up polyatomic ions. Potassium sulfate. The sulfate stays together as an ion. Don't split up the sulfur and the oxygen. Sulfates, nitrates, chlorates, whatever we have that you have to memorize. These polyatomic ions stay together. Do not split them up. Okay, strong acids here. Oh, I should stop. Slow down here. Balance, and then cross out identical spectator ions on both sides and write the net ionic. If you have a strong acid, now where do we have strong acids on our periodic table? HCl, HBr, and HI. For binary acids that would all start with hydro and end in ic, hydrochloric, hydrobromic, hydroiodic. Yeah. These oxyacids, ate to ick, ite to us. Sprite is delicious. I ate something icky, right? Ate to ick, ite to us. Notice you can kind of pick this out a little bit. All of these have 2 more oxygen than hydrogen or more. This one has 3 more oxygen than hydrogen. This one has 2 more oxygen than hydrogen. What's going to happen to these? You're going to get 100% split up into ions. Strong bases, same way. 100% split to ions. Now, what makes an acid? We did naming acids before. Hydrogen, 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 correct? What makes a base? Hydroxide, 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 hydroxide. Drain opener, sodium hydroxide. Do not use drain opener. There's no reason to use drain opener. Here's where you'd ever use drain opener. You invite 200 people to your house and you make bacon for 200 people. And then you dump it directly down the sink drain. And it's going to harden and plug up. Then you could use sodium hydroxide. It would warm up and do it. And for sure, if you have hair clogs, do not do what my psychology teacher friend of mine that knows no science, and he has his own sewer, and he threw every chemical he could ever come across down there to unplug hair. And he ruined his sewer system because he killed all the good bacteria in it. You know, for a clog, you buy this little thing. That's plastic for about $1.99, right? Hair clog in the shower, yes? Yeah, it's gross as hell, yeah? Pull that thing out, it's like snot and big old horkin' snot and hair hooked together, yeah? It's gross. That's what you use. Do not throw chemicals down there. All right, let's do an example here. I've entitled this Ugly Owl. This isn't bad at all, though. This is not Ugly Owl. No, this is. I got to change it. I'll put ugly on the next one, maybe, but this is a pretty owl question. Now, it says, write the net ionic equation for the following molecular equation. Is that all balanced? Oh, yeah. So here's an example. Anything that's aqueous, we're going to split it up. Okay. So if we come, well, we'll do it right here. So we're going to leave zinc solid together. Copper 2 sulfate, we're going to split up and do Cu plus 2 or 2 plus aqueous. Oops, sorry. If you do 2 plus for Al, it just switches it, right? Anybody done that yet? Yeah, Al just switches it. For some reason, I just don't write 2 plus. And then this sulfate stays together. Do not split these up. The sulfate stays together. So we would end up with SO4 minus 2. Zinc sulfate is going to split up. So we're going to get zinc plus 2 aqueous. SO4 minus 2. I better start writing better. Spectator ends. Sulfates. Anything else cross out? No. So we're looking for this. We're looking for Zn solid, and Al's going to want that. Cu 2 plus or plus 2, it'll switch it. Zn 2 plus aqueous. And Cu solid. Now, I want to use this reaction to just introduce you real quick of the last topic we're going to do. So at this point, I just want you to watch. Do not write this down. Just watch, just watch, just watch. Zinc 0. This is a chunk of zinc. No charge. This would be solid zinc that you could hold in your hand. Just looks like it's a metal. This we know is in solution, correct? Aqueous. This is zinc plus 2, and this would be solid copper. So what's really happening here is zinc is giving this copper 2 electrons, correct? If zinc gives copper 2 electrons, we end up with copper with no charge. And if zinc gives up 2 electrons, it would have a charge of plus 2. So we're going to talk about oxidation reduction. And this copper is undergoing reduction because it's going from a plus 2 to a 0. This is being reduced. This is my reduction. And the other one is called, that's becoming more positive, is oxidation. This is oxidation. So that's just a quick introduction to what's called oxidation reduction reactions. And you're just changing oxidation states from the reactants to the products. One of them's gonna go down left on the number line, get reduced, and the other one's gonna become more positive. There's just a good place to introduce that, and you'll see it later. All right, let's do, oh, this is ugly. I'll call this one ugly. Because I don't think it says enough here. So I'm helping you out with this. Write the net ionic react equation for the following molecular equation. Then it says HCl is a strong electrolyte. What does that mean? 100% ions. HNO2 is a weak electrolyte. You're going to get few ions. So let's take it right here. We have KNO2. This is, what is KNO2 called? Potassium, not nitrate, potassium nitrite. Is this going to split up? Oh, heck yeah, that's going to split up faster than Kelsey and Swift. K plus, is that bound? Yes. NO2 minus. K plus and NO2 minus. HCl. This is going to split up. We're going to get H plus aqueous and Cl minus aqueous. Arrow. KCl going to split up? Oh, Taylor Swift, Travis Kelsey again, for sure, 100%. K plus, Cl minus. This does not split because it is not a strong acid. This is going to stay together. That stays together. It is a weak acid. What does it mean to be a weak acid? You get few ions. And if you want more specifics, if you had 100 of these, maybe 6 of those hydrogens come off. Maybe 6. If we cross out our spectator ions, potassium, potassium, chloride, chloride, and we're left with our net ionic. And that is NO2 minus H plus and you end up with HNO2. It's still in water solution, but it's not a solid. All right, another one that's similar that has a weak acid in it. Potassium cyanide, hydrochloric acid. The formula for potassium cyanide. K+1. Cyanide is Cn-1. Hydrochloric acid. HCl, yes. Strong acid or weak acid? Strong acid, right? We know we're going to split this baby. Maybe split isn't the right word. I don't know. Split. Maybe Taylor Swift's next song. Huh? We get potassium chloride. Just KCl. Hydrocyanic acid. This is something you haven't seen before. All the other acids you've seen so far that started with hydro and ended with ic was a hydrogen with a single negative ion. But this actually is this. It's the same as hydrogen cyanide. And the cyanide, it's HCN. Now, let's put our AQs in here. KCN is going to split up. Oh, yeah. Any potassium is going to split up fast. HCl is going to split up. KCl is going to split up. HCN. Are we splitting up HCN? And the answer to that is no, because it is not a strong acid. These are the ones you are going to split for acids. That's it. So you want to memorize these. Unless this is on our test sheet. Now, when we do a test, there's going to be a single reference sheet I will give you. It for sure has those solubility rules. And I don't remember if it has this chart on. I will look as it gets closer. You know, you're not gonna get these ions again. Get off your phone, memorize those. Okay, so we have KCN. Let's split it up right away. So this is gonna be K plus aqueous plus Cn minus aqueous, hydrochloric acid, now we get KCl, which is going to split up. I was able to do this because everything's a +1 and a -1. And the HCN has to stay together. We put aqueous because it's still in water solution. And this stays together because this is a weak acid. And then we can cross out spectator ions. And we kind of have the same thing we did up above. Should take one of these off. Okay, these solubility rules are illustrated here. There's just lots of, there's just like lots of these or some of these have a grid. So I did this grid. I think this is ideal because chemistry is hard enough to teach because number one, you can't trust an electron. And number two, there's just always exceptions, right? I should have been a math teacher. 2 + 2 is 4. No. Yeah, I don't like those math teachers using baby puking formulas. I'll take that back. But there is a difficult, and it's frustrating as a student, and it's frustrating because I'll say, well, that's not 100%. So there's too many things that happen. The electron can do different things. And here's a frustration. This says almost all. This says all. Well, this tells you everything. Now, there is a grid in the back. Here's another table that's all gridded out. That's really kind of nice. The very last page. Mine didn't print correctly. But this is at the back. So if you look at these solubility rules, this right here would say, so this is silver nitrate, soluble, right? You cannot see anything in there. Silver nitrate. What's the rule on that? All nitrates and acetates, chlorates, and perchlorate salts are soluble. Okay, now look at this. Silver chloride. Definitely not soluble. That's a solid of silver chloride. So here, this aqueous, solid, right? So if you go to the solubility rules, this one, doing this out. This one says that all of our nitrates are soluble. Chlorides. It says all chlorides, bromides, iodide salts are soluble except those containing lead, silver, or mercury 1. So that's not soluble. Otherwise, if you have a chloride, boom, 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 it's soluble. This OH, what is OH? OH is a hydroxide. So if you look on the hydroxides are down here, not soluble. Hydroxides and oxide compounds are not soluble except those containing sodium, potassium, or barium. Now, if you look at my grid here, it should match this. So if we look down the hydroxide column, here's my hydroxides. This is a solid. This right here is aqueous, and that's ammonium. Barium is the other one that's listed. And then potassium and sodium. But that's how you kind of look, and you're going to do this for lab. So this is a sulfide here. This is a sulfide and this is a sulfide. So you'd be looking at the rules for sulfides here. And the rules for sulfides are on the next page, number 6. So this one is number 6. Is sulfides. This is hydroxides. This is number 5 down below. Again, in OWL, you will be using these rules. And in lab, your lab manual has these printed out. All right, let's go to this here. We're not going to do this. Does a reaction occur when aqueous solutions of potassium hydroxide and cobalt-2 sulfate are combined? Well, let's do this right up here. Potassium hydroxide. KOH. That for sure, aqueous, it starts with potassium. Cobalt-2 sulfate. Should be aqueous. And that's aqueous in number 4. All sulfates. There are exceptions. And cobalt is not an exception. So sulfates are soluble except those containing calcium, silver, mercury 1, strontium, barium, and lead. Now we're going to switch to positives. So my potassium takes the place of cobalt. So I end up with K2 here, right? I need 2 potassiums. Is that going to be aqueous? Yeah, it starts with potassium, right? So this is aqueous. And then cobalt takes the place of potassium. So we're going to need 2 hydroxides. Hydroxides is number 5. And that is going to be a solid. Now we'd have to balance this. And I would look at this hydroxide here. This is where you'd want to start. You have 2 hydroxides here. There's only 1 here. So put a big 2 right here. And that's all there is to it. Is the reaction going to take place? Yes, 100%, because we've got a solid. If a reaction does occur, write the net ionic. Well, if you are good at this already, you could just go right to it. But I want to write this one. I'm going to write this one out because another liver damage example here. I'm going to have to write it on top. I wish I wouldn't have made that ugly X like that, but I'm going to write the complete ionic up above here. This is going to give me 2 potassiums and 2 hydroxides, right? This is going to give me cobalt +2 and SO4 -2. SO4 stays together. Do not split that up. 2K plus 2 hydroxides. Cobalt. Oh, why did I write calcium? Cobalt. Here's the reason why I wanted to take the time and write this out. This one. What do we get for ions? Get 2 potassiums, right? 2 potassiums. There's no such thing as a K2 plus. Be the rock star in lab and make sure your lab partner does not write this out as K2 plus. There's no such thing. Make sure that this sulfur and oxide is not split up. This is going to be 2 potassiums. 2 potassiums. So this is going to be 2K plus and an SO4 -2. And then our cobalt 2 hydroxide is going to stay together. Now we're going to cross out our spectator ions. Oh, I just wanted to do red. And my sulfates, right? So I'm left with my net ionic there. So we could put that in as 2OH minus. Does a reaction occur when aqueous solutions of ammonium nitrate and potassium sulfide are combined? We can write it out down here. Ammonium nitrate, ammonium NH4 plus 1, nitrate, NO3 minus 1, ammonium nitrate. Aqueous. Potassium sulfide. K2S. Aqueous. Arrow. Switch to positives. Now this time it's the complete ammonium ion. It's the complete ammonium ion, NH4 plus. So over here, NH4 plus. We're going to need 2 ammoniums. We can look that up. And then potassium takes the place of ammonium. So we're going to end up with K plus and NO3 minus. Now, the only way for us to get a reaction is for this to be a solid. And if we look at the solubility rules, sulfides, oh, we got it right here. Ammonium sulfide, aqueous. That is not a solid. It's number 6. Sulfides are not soluble except those containing sodium, potassium, ammonium. So this aqueous, so there's no solids, there's no reaction. Nobody's getting together at the third house party. No, no, no. That concludes our chapter 3, part 1. Now, I think I already said our chapter 3, part 2 does some of this acids and bases here. Because I said you can poke into, I think I said that, yeah. You can poke into chapter 3, part 2 right away. Now, let's review. This is just a chloride ion. If you make it an acid, starting with hydrogen, right? All of these start with hydrogen. Starts with hydro, ends in ic, because this is a non-oxy. Hydrochloric. This is an oxyacid. In this case, I gets changed to us, correct? And then chlorite, I to us again, and then 8 to ic. This is going to start with hydro and ends in ic. This would be, if you make this into an acid by putting a hydrogen with it, you get H2S, hydrosulfuric. So we cranked a bunch of these out already, right? This is sulfite. It's not sulfus. It is sulfuric. Remember, they keep the UR. And this is not sulfic, or this is sulfurous. This is sulfuric, 8 to ic, I to us, 8 to ic. That's what it does. Now, let's look at this right here. Arrhenius definition of an acid. Any substance that increases H plus ion. H plus ion concentration. The generic of that is HY. Y is just a non-metal negative ion. Y can be lots of these, but that's a generic for an acid, starts with hydrogen, and Y just represents a negative ion. Here's the example, HCl, H plus Cl minus. This is a strong acid. It's going to split up. Answer my question. What's the answer to the question? What exactly is an H plus? How many protons? 1, right? If you have the symbol hydrogen there, you got to have 1 proton. That is the definition. How many neutrons? 0. How many electrons? Big fat goose egg. So what do you have? What is H plus? And H plus, when you see the symbol for H plus, it's just a proton. That's all it is. It's a proton. Now, I'll leave you with this. Hold on now. Here's what we're going to do for a quiz. Here's what we're going to do for a quiz. Write this down. Now, the OWL deadlines, I looked at them before class. They're close, but don't wait. Now, you have 5 extra days in Canvas before it completely disappears and it's a 0. So you have 5 extra days. So the due date in Canvas, but you should be working on this as we're going here. Now, let me tell you the quick Taylor Swift, Travis Kelce story. Taylor Swift knows chemistry. So when that SOB cheats on her, she's got a plan. Here's her plan. She knows that electricity will flow through a solution if it has lots of ions in it. So, again, she knows chemistry. She's going to invite Travis over, run the bath water for him, and sprinkle a bunch of salt in it. She's going to use an extension cord from the hall to bypass the ground fault interrupt circuit and throw the hairdryer into the bathtub, which is going to electrify him into a heart attack. She's going to drain the water back out fill it up with regular water and then call the coroner. And then she's gonna write a song entitled Electrify My Love.
Wait, that's.
All right, we will see you on Tuesday.